So it's time to start talking about chemical kinetics. It's our big idea number 5 in this lovely adventure that we're having across AP Chemistry. I wanted to take a moment to make sure that we compared and contrast the ideas of thermodynamics versus kinetics. So where were we and kind of where are we going? Thermodynamics really endeavored to answer the big question of, will this reaction even occur? We boiled it down to being able to calculate delta G, or Gibbs free energy, and that helped us to decide whether or not a chemical reaction was going to be spontaneous or non-spontaneous under a given set of conditions. Our next and last topic is equilibrium, and very similar to how in honors chemistry we used stoichiometry as a method of calculating how much product is going to be made. Equilibrium is what we use in AP chemistry to decide that very same thing. There's a subtle difference here on how the reactions actually take place, and it changes the math behind stoichiometry, but that's what's coming ahead. Kinetics is where we're focusing right now. Kinetics really endeavors to answer the question of how fast the chemical reaction is going to be taking place, and also what factors can I change that might affect that overall rate of the chemical reaction? Like, what can I do to make it go faster? Or, hey, can I slow it down a little bit? So chemical kinetics is really talking again about rate. And again, rate is very, very important. So you're going to hear over and over again in this chapter references back toward the rate of the chemical reaction. And that's simply how we describe either how fast the reactants are used or how quickly the products are made. And overall chemical kinetics, there's a little definition here, but it does have a strange word in here, and that's mechanisms. Mechanisms is again another vocabulary term that's going to pop up in this chapter. And what I'd like you to think in your head is it's kind of a description of what happens during the course of the chemical reaction. Usually you can write these down like an equation. So what particles actually have to bump into each other at the exact same moment in time to create the next part of the chemical reaction. I like to think about mechanisms a lot like Hess's law, where it's a series of steps that occur along the way, but we usually only talk about it in terms of this is what I'm starting with, and then here's my end product. More on that in a little bit. So again, rates. Most of the reactants that we're going to be using in the course of this chapter are all in aqueous solutions. And the way that we measure the amount of an aqueous solution that's there, or literally what quantity, is going to be through tracking molarity. So most rates are expressed as a change in molarity over a change in time. So this presents us with a rather challenging problem here, and that is we need some way of being able to monitor that molarity over time. And there's a couple different methods depending on the nature of our reactants. So one of the easiest ways is if you're tracking either an acid or a base. You can just throw a pH probe on the inside of your solution, and the pH probe obviously would sense the pH of the solution, and you can use that to then calculate the concentration of, say, an acid and how that's changing over time. Or another really easy way is if a gas is either being formed or if it's being consumed, you could actually track the pressure of the container over time as a method of expressing the rate of the chemical reaction. But my favorite uses a technique called spectroscopy, and this you should have seen a little bit of last year, and it's going to become your best friend this year. At the bottom of the screen, you'll see a series of beakers, and they start off being really brownish, reddish, orangish, to all the way to clear. And what you're seeing is the changing concentration of bromine, free bromine, Br2, inside the aqueous solution over time. And you can see as we have less and less bromine present in the solution that the actual color of that solution changes, which means the amount of light that's able to pass through that solution changes over time as well. We can use that difference in the light over time to actually back calculate to its concentration. There's a whole process and procedure behind that. I can't wait to teach you more about it. And again, more on that later. That's going to come up in lab. But this technique where we monitor light as a function of concentration, it's again called spectroscopy. Okay, so we can actually monitor the concentration versus time, and for a lot of reactions, you're going to see something like this. And if you'll notice, this is not a linear relationship. It's actually something a bit more exponential. So we can see then that the molarity is not changing at a constant rate. And in this case, when we look at this, if I wanted to know the rate of the reaction at any given time, that would be change in concentration over change in time, and A is on the y-axis, so that's like the concentration is on the the y-axis, and time is on the x-axis, change in rise over change in run, we would need to calculate the slope at any given point during the course of this particular chemical reaction. That should imply to you, for those of you who are taking calculus, that at any given point I could be able to take the derivative of this particular equation at any given point and actually be able to obtain the rate of the chemical reaction, as it's really just a glorified slope. So kind of weird. Now, the other problem that we're faced with, too, is that since the concentration doesn't change at an even rate throughout the course of the reaction, it would be really helpful to be able to pick a time frame so that we can compare the rates of different chemical reactions against each other. So as a method of convenience, most chemists choose the instantaneous and usually initial rate of the chemical reaction so that they can compare one reaction against another. So again, that's just a method of convenience. And the reason again why is that the rate does not change consistently throughout the chemical reaction. Eventually what we're going to be heading to here is making some equations which will describe the rate of the overall chemical reaction. We call them rate law expressions, and most of the time you can really only find them through experimentation. We will be able to write them by looking at what they call one-step mechanisms. So I'll be able to give you an equation. You'll be able to write a rate law directly from that, but they are rare. Down at the bottom of the screen, it's just trying to show you that what you need to be careful of is that the rate is going to change depending on how much chemical we have. So just like in the previous chapter when we were talking about thermodynamics, that we put delta H in terms of the overall moles of reaction, this is also done the same way. So if you knew, say, like the change in concentration of A over time, say maybe you're changing 2 moles per second, you'd have to look at the coefficients to figure out what your change in B would be. And you can just use straight up stoichiometry to convert from your rate of A to your rate of B. Okay, so now what do these rate law expressions actually look like? So we're first going to take a look at a one-step mechanism. So something as simple as A splits apart and makes B and C. We really don't want to monitor the product so much over time. Usually the convention is that we measure the amount of the reactant. The reason for this is that you can always 100% guarantee the original concentration of A at any given time. Plus, it's a lot easier to measure a big amount of material at the beginning and then monitor slowly how that decreases over time, rather than to measure the appearance of, say, like a B or a C. So we can say then that the rate of this chemical reaction is proportional to the concentration of A. But if we want to make that into an official equation, instead of using the proportionality symbol, and I want to use an equals, I have to put in a rate constant. That is what that little symbol K is all about. It's something that is unique and is very important to put into each one of our chemical equations because it's unique to this particular chemical circumstance. So let's take a look at another one so that maybe you can kind of get the idea. Here's a second example. So the equation is now changed so that there's a big 2 coefficient out in front of your A. And now notice that your rate is now proportional to your concentration of A squared. So our rate law would now become the rate equals K times the concentration of A squared. We would call this a second order chemical reaction. So the coefficients turn into superscripts, and those superscripts are called orders in this particular construct. Again, we have to find these all experimentally, and these relationships are only true for what they call one-step mechanisms. So these particular chemical reactions occur in the beaker exactly as they occur on the page. In this case, it means that literally at the exact same moment in time, two little molecules of A have to bump into each other, and then they instantly form B and C. A lot of the times there's going to be some intermediates, like Hess's law, so we're not going to be able to write these rate law expressions directly from the equation all the time. For right now, we can. We're going to guarantee you that you're going to have one-step mechanisms, so you should be okay. Now, there's quite a few things that are going to affect your overall rate of your chemical reaction. Basically, just what type of matter that you're picking up. In other words, you have to note the thermodynamic state of the system. So your state matters, whether or not you have a solid, a liquid, or gas. Or sometimes you have different forms of the same thing, like an allotrope. So sometimes you're, like, for example, if you're picking diamond versus graphite, the amount of energy that goes into that chemical reaction is drastically different and will definitely affect the overall speed. Some other things too, there are chemical families where your materials are going to behave very similarly, but again at a different rate. So oftentimes magnesium and sodium are going to react in a very similar way in water, but the sodium reacts much, much quicker. So simply what chemicals we pick out drastically changes the overall speed of that chemical reaction. And finally, particle size. So we can do things to try and make things move faster. We can grind up our solids. We can reduce the volume of a solution and concentrate it. Or we can, instead of leaving it in the solid state, add a little water and help the particles bump into each other more frequently. The name of the game here is the more frequently your chemicals come in contact with one another, the faster the chemical reaction tends to be. And of course, again, concentration. So if we increase the concentration of the reactants, it increases the frequency that the particles are actually going to collide, and therefore the chance of reacting is much, 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 much higher. So to summarize, if we have a one-step mechanism, as written at the top of the page, we would start by saying the rate of the reaction is equal to K, the rate constant, specific for this particular chemical reaction, times the concentration of A to its coefficient, times the concentration of B to its coefficient. Now, X in this case would equal 2, B in this case would equal, the Y over B would equal 1. We call X the order of the reaction with respect to A. So we would say, if we were talking about this chemical reaction, that the rate of this reaction is second order with respect to ingredient A, and it's first order with respect to ingredient B. But overall, these orders are additive. So overall, this reaction is considered to be third order.